That is so obnoxiously loud. Okay, so let's finish that one. Say a little bit about what we did last time, and then I want to finish up grading that moment of inertia tensor, and then I want to talk about then going to principal axes where we can then diagonalize the matrix. So I want to do the general theory. I'm going to show you how you can actually whenever you have a symmetric matrix, you can always diagonalize it with the with Octal transformation. I want to go for that one. So what did we do last time? So what do we do? Okay, so we had this little object here, XYZ. And we're rotating it about this axis here. So that's our way we're rotating it. And we wanted to find L. What did we say we do? We treat this as
A collection of point masses.
a collection of point masses. So we come over here to some point R. Here's my little dm here. This. We said that dl equals. Did we say dl equals?
R cross
R cross.
DMV.
Yeah, R cross P. This is our R cross DMV. And what did we do? We looked at the
ith component.
ith component. So we have to look at the ith component of this. How do we write the ith component of that?
W should be a
That should be
IJK.
IJK.
XJ.
XJ, and the XJ is really our
R.
RJ, but for X, I mean for R, you never write it as RI or RJ or RK, that's with convention. This is XJ, which is really the RJ times here DF. BK. Now what do we know about the V? V we know is
Cross
there is an R,
omega cross R.
the omega cross R. So we put this in here. So we had this epsilon IJK, XJ, DM. I need the kth component of this. And what's the kth component of this?
W should be a K
ARS.
Omega R.
Omega R.
That's
XS. Then we beat on this a lot. I'm just going to jump to the result. His reaction repeats a very similar derivation for reading kinetic energy, so I don't go too bad about that. And what did we end up with? We ended up with this. We ended up with this I J omega J, where this actually, let me skip a little bit more. We have to integrate this with the LI here. So if we add these all up, we get this. And this LII ends up being, by definition, this DM. What did we have then?
Connected delta IJ R squared
R squared
minus XI XJ.
XI XJ. Okay. And this is our moment of inertia tensor, which looks a lot different from what we had in the first semester. 125. It's actually a tensor anymore. So again, it's always hard in general physics where somebody will say, was that I a scalar? Let's not ask what I is. Let's just go on. Because they're not ready for tensors. They can't handle the truth yet. To them in their little world, there's only vectors and scalars. They don't realize that what's out in the big wide world yet. Okay, so that's what we had. And then the one thing you can see with this is what this is going to mean here when we write it in terms of a matrix, like this, is that the direction of omega and the direction of L need not be the same. Okay. So our L vector for this right here, our L vector when we actually work on this, might actually go like this. So when this thing rotates, that L vector is going to rotate about here like this. These don't have to be in the same direction. And actually, when they're not in the same direction, that's going to give rise to a really complicated motion. Usually it's not good motion. If devices if usually when you have like anything spinning, you want these two to be aligned. We'll see why later. Turns out if they're not aligned, then usually that device is not gonna last. It's usually gonna be quite bad. Okay, questions? So we started calculating one of these. Now we said this is when we have a continuous object, and just so you know. Usually what's gonna happen is that this DM here. We're gonna usually have the density of something, so we're typically gonna write this as the density of the object. Okay, times D3R. What would be D3R?
X, Y, and Z.
Yeah, so what this is gonna be, this little guy here, if you'd actually look at this column here. This would be something more like this. This is what our DM is. And this would be our dy, this is the x. And this is our dz, so d3r is dx, dy, dz. Your density is mass over volume. So your mass, your dm, is over your volume, your d3r. So your dm is usually, well, usually is density times your volume. And this is normally how we go actually calculate these things. And often this could be a first class pain to actually calculate. And how many of these components did we say we need to calculate? Because we said this matrix here, what kind of matrix is it? It is
Symmetric.
sure.
Symmetric.
This is a symmetric matrix. So how many components did we actually need to calculate?
7.
We had to calculate 6. Okay. So we have to do 6 integrals. So that can sometimes be about as much fun as you think doing 6 integrals in some D. But that's what you have to do. Okay. So we're actually doing a simple case here when we just have point masses. And we said when we have point masses, we no longer have an integral, we have a sum. So for point masses, and the only reason we're doing point masses is because it's easy. So we said for point masses. So for an object composed of point masses. What do we have? We're going to have this guy here is going to be a sum from k going from 1 to n. And that's going to be the number of point masses here. We basically put k's on everything here. So we have this delta ij, r squared with the kth particle minus xi for the kth particle, xj for the kth. And then there should be an mk there that I dropped. Okay. So we took the simple object last time of this. This is M. This is big M. This is B. Big M. This is A. What do I feel like this? I can imagine these are massless rods connecting here. And so the question is, what is the I for this? And so we did the I11 last time. So last time we had I11, and this I11 was little m, little m, b squared plus big M. Actually, what did we have?
We had little m b squared plus big M b squared.
There has to be an and there too. Did I drop it? Oh, of course, because it's yes. So we do that there. That makes sense. Now, why does that make sense from what we did in first semester physics? In first semester physics, what do we say the moment of inertia is? If I clap my hands and make you all freshmen again, you can find your little beanie, your little propeller, little sock monkey, your little fudgesicle. Watch reruns of Scooby-Doo and go back to your little dorm. What do we learn in general physics that the moment of inertia is? So in 125, I is what? It's just sum on I, m I, r squared. Where did this R go from? It's the perpendicular distance from the rotation axis. So in this case here, if I'm doing I11, what's going to be my rotation axis?
B.
This is going to be the X rotation axis. And so what you're going to have here. So in 125 language, it's this. Okay, so here's my rotation axis. For the I11, in other words, IX. What we do, we have this mass here and then this mass here. Okay, so this is bigger, this is M, this is lower. And so what's the R for each of these cases?
0.
0. Now, what is the R for this guy here?
B.
Yeah, this is B. So this guy here would have MB squared. And what do we do? We have this little A, this little arm here. And what is this distance here? Because it's that, this again, it's that perpendicular distance we have. This would be
B.
little MB squared. So what do? This is going to be within the sum of these two. So this is what we would have in 125. Does that make sense? Questions with that? Okay, now let's do I22. Okay, so I22 is going to be what? Let's go through and actually calculate this. So this is going to be sum on K from 1 to let's see 4. This would be MK. I'll call this N. Okay, this is going to be delta 22. Delta 22 is nothing but 1. And so what is my RK squared? This is going to be XK squared. This YK squared. This is AK squared. Okay. Minus, and then one of these through here. This is going to be Y, Y, K squared here like that. What does that equal? That term cancels this term. And this is the Does that make sense? Let's do it the formal way, then we'll see that the 125 way we could actually just write on the answer immediately. Okay, so what does this become? We gave these names. Was this 1, 2, 3, 4? Yeah. This is 1, 2, 3, 4. If we look at 1 here, I have M. Okay, what are the X and Y for that one there? X and Z, they're both 0. So this is 0 squared. This is 0 squared. So this is basically the first mass. Plus the second mass is big M. So what's X squared is?
A.
Okay, so this will be A squared plus 0 squared. This is going to be by 2. By 3. No. Oh. Particle 3 is going to be what? Little m.
A squared plus 0 squared.
What's to be A squared plus 0 squared? Then I have my little. This is my particle 3. And then what is this one?
0 squared plus 0.
My X value is for this guy. 0. My Z plus 0. So what do we end up with? We end up with this I22. It's just going to be nothing but M A squared plus little m A squared, or little m plus big M A squared. Why does that make perfect sense for 125? If I'm calculating I22 and 125, what is my rotation axis?
Y.
It's the y-axis. The 125. Right. This is my y-axis. So which way do I have? This guy, this guy, this guy, and then this guy. And this right here, this is my A, that's my perpendicular distance here. This is my A, that's my perpendicular distance here. So I'm getting a 0 here, a 0 here, and then this one's giving me a big M. So I'm getting a big M a squared from this. And this one's giving me a little m a squared here. That moment of inertia, what does it tell you again? It tells you basically how your mass is distributed about the axis of rotation. So the further away the mass is from the axis of rotation, the higher the I. If that mass is closer to the axis of rotation, the smaller the I. Right? That's what that tells you. It tells you how close that mass is to the axis of rotation. What happens for IZZ? Let's just write down a fat. Let's kind of, because I don't want to just do this on. I want to get to the some symmetric matrix. If I just say calculate this by a 125, what would you say IZZ is? So what's my rotation axis now? That would be my rotation axis, right? And so what would be the contribution then from this guy here?
0.
0. So to get m 0 squared. So this is no 125 really. What would this one be?
A squared.
That'd just be a squared. That is my that friend here.
B squared plus B squared.
Yeah, this is going to be my distance here, right? That's my perpendicular distance here. So that one's going to be what's the little m a squared plus b squared. Then my little friend here. And that's my perpendicular distance here. So that's it's just
B squared.
big M v squared. So what does this give me? This gives me little m plus big M a squared. This little m plus big M a squared, or little m plus big M a squared plus b squared. Now that's what you do in 125. Now that we're all grown up, now we have brand new terms. And what are the new terms we have? The off diagonal pieces. Okay, so and that's something you don't get in 125. You don't put the off diagonal pieces in. So basically in 125, you just deal with the diagonal terms of that moment of inertia. But you don't know that at the time. Okay, so what about the off diagonal pieces? This guy here. What does that now become for the off diagonal pieces? What do you know about the I and J?
They're not equal.
Yeah. So I is not equal J. So in this case here, the off diagonal pieces becomes what? It becomes this term is now 0. So this is minus. So I'm giving this minus sum on k. Mk xik xjk. That makes sense? Now, in this matrix here, which term can we now collect? We don't even have to bother with them. I'm thinking about this problem here. Which of the off diagonal terms do we have to worry about? And which can we immediately write 0? Close. What you know about the z component for each of those quadrants? This is an xy plane, so all those z components are 0. Therefore, which off diagonal terms do we not have to worry about? Anything with which number is the z-axis? 3. So anything with a 3 in it. You're gonna have to have the 3 in here after be 0. So since our masses lie in the XY plane, the Z's are 0. So therefore, I13, I23 equals 0. But what about I31 and then I32? They're still 0 as well. So that means we have to worry about what?
2, 1, and 1, 2.
Yeah, and which one of those do we have to worry about? You have to worry about both of those? Because
Symmetric.
we have a symmetric concept. So I always start lower and go higher, so I'm gonna do the I one too. Okay, so I12 is going to equal what? Sum on K, MK, X1K, X2K. In other words, the sum on K, MK, there's a minus sign there. XK, YK. So what's my center guy? Zero. Zero. Right, this is 0 from 2. Now, so the 2 minus big M.
For 0.
A times 0, which is also 0. Let's do my third guy, minus little m.
A times B.
AB. Plus my little guy, my fourth guy, minus m. Zero times speed. What happens here, my I12, which is the same as I21, is minus little m AB. So what this means here is that my I matrix is blocked. Okay, what were these again? This is little m plus big M e squared minus MEG 0 minus MEG little m plus big M e squared 0 0 0 little m plus big M a squared plus b squared. Okay. Make sense? So if omega equals 3 I hat, what's 4 j hat? What is L?
Using the.
Okay, so how are omega I now all related? L equals I omega. So what do I have? I have this L equals I friend here. What did I put down for omega?
3, 4, and 0.
This would be a 3, 4, and 0. What does this end up equaling?
3 times m small m plus big M e squared minus 4 m a blue. Minus 3 m small m e b plus 4 small m plus big M e squared. 0, 0.
Is L along omega? I mean, is this L some multiple of my omega?
Yeah.
And I pull terms out and write this as a column vector 3 4 0 some overall constant. Can I write L is basically some factor of omega. This is a constant. Absolutely not. Nothing factors out of there, so you can't do this. The answer is no. So what happened here, that means that I don't know exactly how this will go. This would mean that this L vector goes like this. Okay, and the omega vector would be something, who knows what, maybe like this. Okay. And so what's going to happen is that if we rotate about this axis here, this L is going to change. Now, if this thing starts to rotate, what's going to happen to my eye? So here's my axis here. Start spinning it around this axis here like this. What's going to happen to my eye?
It's not going to be the same.
It won't be the same. My eye is going to change. Okay, so this becomes a pathological mess. Now I'm going to show you how to deal with this, but we're not quite here yet. That makes sense? So what this is we calculated L for this time here when it's like this, when it's in the XY plane. As soon as those particles leave the XY plane, my eye now changes. It's a bigger mess. Okay? That makes sense? Question to that. All the things with rotation are just really, really complicated. Turns out, for those of you taking general relativity, it turns out when you do rotations in general relativity, it turns out to be a lot worse. Because what's going to happen is that this is so design. When your object is spinning like that, it literally takes the space and time around it and starts moving that as well. So your space actually starts being dragged with your object. And that's going to give rise to really bizarre physics when you go inside a rotating black hole. The rotating black hole is called a curved black hole, and we're going to go inside it. And it turns out the structure of the rotating black hole is a lot more complicated than a stationary black hole. And we'll go into this. I don't recommend going into either black hole, stationary or rotating, just don't. If you had to go into one of them, go into the rotating one. You have a chance of surviving. Going to the one that's not rotating, you might, depending if it's big, you might live for quite a while. But you're ultimately going to die. Okay, you don't necessarily have to die in a rotating black hole if you're smart with your spaceships. It need not be fatal. You're not getting, well, you can get out. Again, depending on where you are. Okay. So often it is useful to use a coordinate system where I is diagonal. And what did we call that coordinate system on Monday? The what axes?
Principal.
The principal axes. So these this coordinate system is called the principal axis. And I want to show you how to find them. So how do okay, so first of all, we need to know a little bit about linear algebra. So sidetrack and go to linear algebra. So we need first we need some theorems from linear algebra. Here's going to be the theorem. We're going to prove each of these here. Okay. Theorem one. Okay. The eigenvector of a symmetric matrix or now I'm going to use the word there that you haven't had before. Okay. What does it mean to be an eigenvector or eigenfunction or eigenvalue or eigenvalue? Is that let's see, U3, U4 I've had modern, U4 I've had modern. And so we've heard those words before. I don't know if you two have heard these words yet. You may have not heard those words. Okay, so let's do a little back up one more step. What does it mean to be an eigen function, not vector, again, function, eigenvalue? Right, for those of you taking modern, we're going to be, this is basically, you don't do quantum mechanics without this. Okay, so U4, you tell me what you know about that. What does it mean to be an eigenfunction?
You have an operator
You have an operator,
acting on your eigenfunction.
acting an eigenfunction. What do you get back?
You get your eigenvalue and your eigenfunction back.
So you get the function back multiplied by a constant. So we're going to let O be an operator. And how do we denote an operator? We always put a little hat on it. So let O be an operator. That acts on a function. So let's do some examples of an operator. Okay. The operator here might just be a regular derivative. Right, if you say d by dx, that has to act on something. That's why it's an operator. Oh, we could say that maybe O is a second group. Maybe it's a partial like this. Okay. It doesn't really matter what the operator is. Okay, it's going to be something else. Maybe it's not even something like this. Maybe it's the parity operator, where you're going to take x, y, and z and replace it with second minus y minus c. Could be anything like that. Okay. So what happens? Okay. So if O acting on F gives F back multiplied by a constant, F is called an eigenfunction. And the constant is called the eigenvector. Okay, so what this means here is that O is gonna act on F. We get the F back, this is the same function, and then we're gonna have a constant here, the constant is almost always called lambda. So lambda here's a S. Lambda is the eigenvalue. And F is my eigenvalue. Okay. Let's take some examples here. Okay, so we're gonna say, this is my O. Okay, let's say is that equals sign up X. Okay. So if that's my operator, that, you know. No, right, because you'd have O acting on F, so that would be this. Okay, this should give me cosine of X, and this right here is does not equal X. Just not an function. Okay, but what about F? If F is equal to, let's say, 4E and the 2X. Is that an eigenfunction? Yeah. Because if I have this. What's that equal? Well, okay, this is gonna be O acting on 4E to the 2X, which equals
8e to the 2x?
8E to the 2X. Okay, what's the eigenvalue?
2.
It's 2. Why isn't it?
Yeah.
It's 4 as far as the
Original. F is fucking my original function here. Why? Because I wanted to just illustrate the point. So this 8 is really 2 times 4e to the 2x. It's right here. And these are the same. And this right here is my constant, so this is my. Okay. Now, what do you think it means to be then an eigenvector? You're doing now with linear algebra. What do you think our operator now becomes?
Matrix.
An n by n matrix. And that's going to act on a vector which we write as a column. In linear algebra, what's going to happen? So in linear algebra, O is a n by n matrix. I'll write it like this. And F is a column. Okay. This F moves about that. So we're going to have in that case. So this O X and F, I'm going to get lambda times F. In this case here, then you call this an eigenvector. Okay. This is what we want to show. This is going to be actually easy to show. Well, once you know how to do it, once you see enough of these proofs, it's always the same. So in our case, let's ask what happens when O is a symmetric matrix. What does it mean to be a symmetric matrix again? Take O.
Transpose.
Take the transpose, and this is going to equal
Yeah.
O. That's what it means to be symmetric. Now, for those of you taking quantum, let me just, okay, this is part of conversation with the quantum people. You're gonna basically have the exact same thing in quantum mechanics. The difference is that this always gonna be complex. Meaning having an I there, not just complex metaphysically, but it's gonna have an I in there very frequently. And what you're gonna do, you're gonna take the transpose and, so this, don't write this down. So for those of you in taking quantum, you're gonna do this, and then you're gonna take the complex conjugate of the whole thing. This whole combination here is called the dagger. So the way you write, it's called the dagger. What this is gonna be is you write the dagger like that. And so in Macbeth, you know, is this here a dagger I see before me? Okay, it's actually a metaphor for dealing with matrices like this. You're so happy. I know, it's shocking. Okay, this has been called permission. Okay, so the quantum analog of symmetric matrix is permission. Okay. And the quantum analog of an orthogonal matrix is a unitary matrix. Because what's going to happen there is that if you take the dagger of a matrix, if it equals its inverse, then it's unitary. In this course, where we don't have the complex piece, we take the transpose, and then if that's the inverse, it's another orthogonal. But it's the same idea. Once again, illustrate that clearly linear algebra is far more fundamental than differential equation. But again, no one will agree with me on that, even though I'm correct. And that's fine. Okay. Now I'm so clear. Okay. So what I want to do is this. Okay, so the claim is, here's the one. If O is symmetric, the eigenvectors of O are orthogonal. Meaning that VI transpose times VJ equals 0. Okay, where VI and VJ are eigenvectors of O. So this is what it means for your father. Let's do the proof. The proof is actually quite limited. So proof. So let VI and VJ be two eigenvectors of symmetric matrix O with distinct. Okay, they haven't taken a bath in a long time, they just distinct. Okay. With distinct eigenvalues. And I and language J. You can actually relax that condition, but it's a slightly harder proof, and I don't want to do that. Because I feel like being busy. You have to do something slightly selfish, consider this an idea. So let's write down what this means. This means that with O acts on VI, which we get, that this is an eigenvector. We have to get VI back, but this one's going to have an eigenvector of, I mean, an eigenvalue of
Lambda.
I. Okay. When O acts on VJ, you get VJ back times
Lambda J.
the J. So that's what it means. Now the claim is that these two vectors are going to be orthogonal, meaning if I take the transpose of one times the other, you're going to get 0. Okay. Proof.
Do you multiply by 1?
No, we're not going to, but never a bad thing to do. Okay. So I'm going to multiply the first equation. By V J transpose. Then take this equation here and multiply both sides by V J transpose. And this type of proof is used a lot in physics and in mathematics, so it's one of those proofs you might want to really know. Gee, I wonder if my cats are going to put it on their third test because it's so fundamental. We know the feline brain. Okay. There. Okay. Now we have to make use of the transpose part. So what do you think we're going to do to both sides? Take the transpose. Take the transpose. And get V J transpose O V I transpose. That's equal lambda I V bar J transpose V bar I transpose. Okay, you tell me what's going on. What's going to be the transpose of my buddy here?
VI transpose.
VI transpose.
O transpose.
O transpose.
J.
Yeah, the transpose of a transpose undoes itself. So this. Now, why did we do that? Because when you take the transpose of things being multiplied, you transpose each of the individual things, then what do you have to do? Reverse your order. Equals lambda I, and this, notice, there's a spot right here that I needed this, but due to the limited blackboard space in the Science Center, I was forced to erase that. You did not. Okay, then what does my buddy here become? My buddy here becomes
VJ.
V I
VI transpose.
VI transpose VJ.
VJ.
Because the transpose of the transpose undoes itself. What on earth is this? When OX on VJ. VJ is a
Eigenfunction.
eigenvector of O with eigenvalue
Lambda J.
lambda J. So this right here is lambda J. V bar J. Right. So this is the constant, so we're going to pull that out. So here this is lambda J, V bar transpose, and VI transpose VJ. This equals lambda I, V bar I transpose VJ. Now you have to be very careful here. What is the tempting wrong thing to do?
Say lambda J with lambda I.
Why would you say that? Because you've done something. I mean, you're right, just kind of put in the bells. How did you come to that conclusion? Okay, why did Jake say lambda I equals lambda J when I said what's the tempting wrong thing to do? And he's right.
It's canceled.
Yeah, I said, same. You're done. Lambda I equals lambda J. Okay, you can always divide the equation by like terms with one exception. When can you not divide? You can never divide an equation by
0.
0. So you have to be a little more careful here. So let's actually be a little more careful here because we don't know what this combination is. Maybe it's 0, maybe it ain't. So I'm going to take this over to the other side. This. Now I can factor out this term here. Now I can factor this. I can write this as lambda J as lambda I times V bar I transpose V bar J equals 0. Now, what do we know about this? What do we know about lambda I and lambda J?
They're different.
They are not equal to zero. They are distinct. Hopefully tonight they take a shower, so they will be just good. Okay, maybe not. Okay, so then what do we know about this? The only conclusion is that this piece here has to equal zero. Now, why do we call this thin orthogonal? For very good reasons. What is this an example of when you read it like this? This is the matrix form of a dot product. When you take a dot product, you have the terms equal to zero. When those two vectors are perpendicular, when they are orthogonal. So this looks like a dot product. Okay, and the dot product equals zero, and the two vectors are 90 degrees. That's why it's called orthogonal. Okay, so that's the first thing we need. I'm gonna stay with the next one is, and I'll prove it next. I'll prove it on Wednesday. You know, we need that rotation matrix to basically rotate a vector. And what I'm going to prove tomorrow is that rotation matrix here, A, the transpose of it here. What we're going to put in here is that this is going to be my first eigenvector. This right here is going to be my second eigenvector. And this right here is going to be my third eigenvector. That's how you construct that. That's not one bit obvious. Okay. So what I'll do for the proof tomorrow is I'll try to convince you that if you do this, this is actually how we have to transform them. So if you remember what happens here is that our I matrix transforms according to this. And we'll go back over this one tomorrow. And if I want this to be diagonal, if I do this, yays, that will make that matrix diagonal. So what happens here is that this, and this, they are my principal axes. This will be my new x, this will be my new y, this will be my new z. So they're going to be the new principal axes here, but we don't know that yet. That's where this is going to. Okay. So from that coordinate system, our I will always be diagonal. There's a reason why. I mean, normally what should happen now is that we should be doing central forces, two-body problem. There's a reason I'm not doing the two-body problem now, because if not, this gets pushed off after break. And this is a subtle concept. And the last thing you want to do after break is basically dealing with this extreme subtlety coming in. Okay? Because this is actually remarkable. Okay. Have a good day.